This is the most in-depth breakdown of designing a messaging app like WhatsApp from scratch that you will be able to find on the internet. Messaging apps like this show up all the time in senior and staff level interviews, and that is because they force you to handle stateful connections, think about real-time delivery, consistency and scale of the system, failures of pieces of the system or overall disaster recoveries, and multi-device sync in case of users using multiple devices like mobile phones and desktop apps. So in a short interview, you need to show that you understand not just the happy path, but also all the things that can go wrong in messages when they are flying around between disconnected users and mobile networks. And we are not going to ignore the hard parts and pretend that everything just works without us preventing the failures. So we will start by first building this from scratch, starting with a simple version that works for a few thousand users. Then we'll scale it up to handle billions of users sending messages across unreliable mobile networks. And after that, we'll identify where it breaks and how to fix it properly. At the end, you'll also find the full set of footnotes explaining every technical concept that I mentioned while designing this, so you can revisit anything and you can go deeper on each topic. So let's see what we are going to cover in this video. We'll start with a very high level architecture of the system. Then we'll choose between the connection types that we are going to use, like WebSockets or long polling or something else. We'll cover the service discovery architecture and how we are going to set up a load balancer here. Next, we'll design the data model in short, like how we are going to connect different databases together and different tables together. And then the WebSocket and REST API designs, also the sequence diagrams on how users are going to send messages to each other. After that, we'll cover the message flow when both users are online and also when one of the users is offline and how we are handling these type of situations. Then we'll solve the group message fanout problem where we have, let's say, 50-person group in the WhatsApp chat. Then media handling and how we are going to use pre-signed URLs to do it the right way. After that, we'll get to scaling, adding message queue to the database cluster architecture, and also cover the message storage service where we are going to process the messages. Then we'll cover some of the security aspects like end-to-end encryption, rate limiting, strategies to shard the user ID and replicate the databases, database replications per shard, scheduled jobs to clean up the infrastructure, cache failures and dual write patterns, multi-region and cross-region message flow, disaster recovery with Kafka cluster, and feature flags to help us ship features with controlled environment from the backend. Now, before getting to the high-level design and sketching diagrams, we need to start always with the requirements to understand what we are building here. So the core requirements that we have is that users need to be able to send and receive messages in one-on-one setup. So on top of that, we also have group chats with up to 100 participants that we need to support. And messages are delivered not only when users are online, but also when they are offline. We need to handle that scenario as well. They can attach media files like images, videos, or audio clips like voice notes. We need to track the statuses of messages, like when they are sent, when they are delivered, and when the message is read from the second user. And of course, we need to track the online-offline status to show them the last seen date of when the user was online. These are the core requirements. When it comes to non-functional requirements, we need to provide low latency delivery, so under 500 milliseconds when users are online. We also need guaranteed message delivery, so of course messages can't just disappear and not reach to the second user. In the scaling phase, we need to handle billions of users with high throughput. And to keep the storage manageable, we don't store messages on servers longer than they are necessary. So it needs to also stay resilient when individual components fail. Let's say one of the components fails, like the server that needs to push the message to the second user. We need to handle these scenarios as well to make sure that the user eventually receives the message when the server is back online. With that, we can do some back of the envelope calculations to understand the scale of the system, and then we'll start with the high-level design. Let's start with user metrics. We have at the scaled phase 1 billion registered users and 500 million daily active users. During peak hours, it will be handling 50 million concurrent connections, and on average, we will expect to have 10 to 20 messages per user daily. With this, we can start the message estimations. For example, for the daily messages, we need to multiply the active users with the average daily messages that will be sent, which is 20 at max, and that will be 10 billion messages sent every day in the system, which means 10 billion writes to the database every day. That comes down to 115,000 messages per second on average, so 115,000 writes to the database. And during peak hours, we can expect to get 3 to 5 times more of the traffic than on the average, which will be 350 to 500,000 users writes on average per second. Now let's also estimate the storage. So each message with metadata, let's just consider it to be 1 kilobytes. It should include the text content, the server and receiver IDs, the timestamp when the message was sent, and the status flags. Since we have 10 billion messages per day, it will be 10 billion times the 1 kilobytes, and we will be storing 10 terabytes of storage per day for the messages. And on annual basis, this comes down to 3.6 petabytes per year, which is 1000 terabytes for each petabyte. And the bandwidth will be 50 million concurrent connections at the peak traffic time, and each connection will average out to 10 kilobytes per second for active messages, which comes down to 500 gigabytes per second of bandwidth. One important thing here is that most messages get delivered and cleared from the server within seconds. So we are not going to store this everything forever. Users download the messages to their devices and also backup if they want to, for example, to Google Drive. And then we can clean up the server side to not store any unnecessary data. Here in the beginning of requirements, we have to set it to be stored for 30-day retention for undelivered messages, and maybe let's say 10% of users keeping history on servers. So this allows WhatsApp to run on minimal infrastructure because they are very efficient about not sending the unnecessary data. Now with these rough calculations, we can start with a very high level design of what the system will look like. Let's start simple and add complexity only when we will scale to more users, but for now this is the initial setup. We will have the mobile app, which is the client, like the user's phone. It is responsible to maintain a consistent connection with the chat server, handle the UI, and manage the local message storage, and also retries when failed operations happen. The next piece is the load balancer, which sits between the mobile app and the chat servers. This will be responsible for routing the incoming traffic between multiple chat servers to handle the peak load and traffic. These chat servers will maintain a WebSocket connection to the client, persistent two-way communication channel that will stay open, and they will route messages between users and track who's online and handle messages persistence. Then we'll introduce a message queue, which will be for decoupling message writing from delivery. And this is also one of the things that will allow us to handle the failures. So when one of the chat servers receives the message, it will immediately acknowledge and tell the mobile app that the message was sent. And then it asynchronously pushes the message to the message queue for storage and delivery. And as an example, this can be either a Kafka message queue or RabbitMQ that will work here. Now this message storage will consume that message that is coming from the server, from the chat server, and persist it to the message storage database. As a database solution, NoSQL will work better here, something like Cassandra or DynamoDB, because we need high write throughput, as you saw in the estimations, and our query patterns are mostly straightforward. We will be fetching messages by user, by conversation, or by timestamp. And since we're writing billions of messages per day, we need something that can handle the massive write volume without slowing down. And that's why something like Cassandra or DynamoDB is the best fit here. Next, we'll need also some user connection cache, something like Redis, which will be tracking which users are online, which chat server they are connected to, and their last activity timestamp. This will help these chat servers to make the routing decisions faster, because checking this Redis storage takes something like microseconds versus querying it from the database, which will take milliseconds. And at scale, that difference really starts to show up. In the requirements, we also have the requirement to store media files like messages with voice notes or with images. For that, we will use some sort of blob storage. This can be like the AWS S3 or Google Cloud Storage, and this will be storing the media files and hold the actual files. But then we will also distribute this to a CDN network, which will cache the popular files at edge locations worldwide, so that downloads are fast regardless of where the users are, because one user might be in US and the second user might be in Europe. And in this case, you will have the same copy of the file in Europe region as well. And for the Europe user, he will download it from the CDN, which is closer to his location. Next, we need also a notification service. This is mainly for the offline users, which need to receive the notifications either through Apple Push Notification Service or Firebase Cloud Messaging for Android. And when someone messages you while you are offline, like let's say user A messages to user B, and then user B is offline at the moment, they will receive instead the push notification, and then later they can read the message when they open the app. And lastly, we need also a dedicated presence service, which will be used for managing online and offline statuses of the users. Let's say user A again is online and user B is offline. This presence server will receive the heartbeats from users, updates from the Redis, and also publish the presence changes to the interested subscribers like the user A, which is interested whether the user B is online or offline. Now let's choose the communication method between the mobile app and the services, the chat servers. We have three options here: polling, long polling, and WebSocket communication. Of course, most messaging apps use WebSocket for communication, but let's understand why is that the case by looking at their pros and cons. Let's start with the polling option. Let's say you have the client on this side and then chat server on that side. With the regular polling option, this is how it works. We will do periodic polling from the front end to backend, asking whether they have any new messages or not with some API endpoint. And then let's say we don't have any new messages, so this will be an empty response saying that there are no new messages in the server. And then from some time again, we will also need to query the same thing and ask whether there are any new messages. And then let's say for the second time, there are new messages, so they will receive the messages that they received. This, as you can see, wastes a lot of bandwidth and adds latency, because if you're checking every 2 seconds and the message arrives right after you check, you wait 2 seconds to see it while you could get it instantly. And if you also multiply that by the millions of users constantly asking for updates, even when there is nothing new in the chat server, you're burning a lot of resources for no reason. That's why one better approach than this is the long polling option. In this case, we wait for the new messages or timeout. So let's say we request the new messages from the server, and then the chat server will wait for some time until the timeout. If there are any new messages, it will push them back to the client. And if there are no new messages, then after some timeout, it will push the response, which will be again an empty response saying that there are no new messages in the chat. And if there are no new messages, then this needs to again query to the chat server, and then basically this process occurs again. This is still problematic because you're constantly opening and closing connections, and each message requires a full HTTP handshake. At scale, this is again an overhead because your chat servers spend more time managing connection lifecycles than actually delivering messages. Plus, there will be some idle HTTP connections like in this one where they are waiting for the response, and they will consume the server resources like memory for connection state and thread pool slots without the efficiency benefits of WebSockets. That's why most of the chat services work with WebSocket communication. This is one persistent bidirectional connection between the chat server and between the mobile app. So client and server can both push data at any time. First, client will initiate the HTTP connection with the server, and then they will perform the WebSocket handshake. And after this point, the connection is established and it is persistent throughout the session. This way, let's say user A sends a message to user B, which is this user. Server is able to independently push the new messages to the user B, which received the message. So push the new messages as soon as they are available. And also the client, which is the user B, is able to send message or acknowledge anytime without making a new connection. And this connection is persistent and allows real-time bidirectional updates both from the chat server side and from the client side. The trade-offs of WebSockets is that it requires special load balancers that support them. So we'll need to use layer 4 load balancing instead of layer 7. They also use more memory per connection on the server side because you're keeping connections open, but it's still worth it because of the real-time messaging and the latency of the message requirements. Next, let's see how we are going to manage the chat servers which are routed through the load balancer. In production and in reality, chat servers come and go. They will crash, get deployed again, scale up and down. And how does the system keep track of what's available? So the problem here is that the load balancer needs some way to know which servers are available, like chat server 1 and 2 are available at this moment, and chat server 3 is unhealthy. Let's say it either throws timeouts or it's throwing errors on requests. So one solution that we can use here is service discovery cluster, like a service registry similar to Consul or AWS Cloud Map. And here is how it will work. Whenever these chat servers start, let's say this server 1 boots up on some IP address, it will register itself in this service discovery cluster. And after that, we will do health checks every 10 seconds with this server 1 to see if the server is up and running. And then similarly, we'll do that for server 2 and server 3. And now let's say the load balancer needs the list of available servers. It will first query the healthy servers from the service discovery cluster, and then the cluster will send the server list to the load balancer. With this new list, let's say we forwarded only the IP address of the chat server 1 and 2. So the load balancer will be able to update the routing table and then route all the traffic only to server 1 and to server 2. And it will know that server 3 is removed from the routing, so we are not making any requests to the server 3. That's how we will manage the load balancing and traffic routing. Now let's move on to the data model and designing the data tables that we will have, the primary ones. We will first need a users table, and this one can be actually stored in a SQL database like PostgreSQL or MySQL. So the user will have an ID, which will be the primary key, then a phone number, which needs to be unique for all users, then a username created at, which is a timestamp, and last seen, which we will use for controlling and showing to the other users when this user was last online. And of course, more fields will be here, but these are, let's say, the primary ones that we will need. The next table will be messages, which is the table in Cassandra, actually, where we will be storing messages. Since this is a high volume database, we will be writing and reading a lot of messages from. We will need the sender ID here, which is the connection with the user ID from the users table. We will need the receiver ID, which is again a connection to the same field in the users, and a message ID, which will be the primary key for this table. Apart from that, any other things that relate with the message, like the content, which is the text, media URL, if we are storing any voice notes or any image video files, the status of the message, which will be either sent, delivered, or read, the timestamp of when this message was delivered, and whether it's deleted or not, because they are also able to delete messages on WhatsApp. For managing the groups on WhatsApp, we will also need groups and group members tables, and this can be again in the PostgreSQL database. For the groups, we will need ID for each group, which will be the primary key, which we will use for identifying the group, the name of the group when it was created, and who's the user that created this group. And then this is a one-to-many connection with the groups and group members, where we will be adding new members, and this is the ID of the group where they are added, the role of each member when they joined, and the user ID, which links to the users table, user ID, and that's the primary key of users. Apart from this, one more important thing is to have user connections registry, where let's say these can be stored in a cache like Redis. This will store the user IDs and the server ID where they are connected to, also the connection ID if it is open, last active time, and device type. And we can add this to the Redis cache and then update every, let's say, 300 seconds to refresh it with each heartbeat. Once we have the database row schema, we can move on to the API design, specifically for WebSocket and REST API flows for the messaging app. The first step from the client will be to authenticate with the server by sending the user ID, the token, and device information. If it is successful, the server will respond with auth success, sending the session ID, the server time, and the unread count. After that point, the client can start sending and receiving messages. Let's say it sends a message to the receiver, so it will send the information about who's the receiver, the user ID, the content, the media if there are any, and the timestamp of the message. And at this point, the WebSocket connection is already established, so there is a bidirectional communication, which means that server is also able to push messages or acknowledgements to the client. So it will acknowledge, for example, when the message is received. It will also deliver any new messages that there are from other users, like the message ID, the sender, the content, and the media files. And then client will be able to also acknowledge when they receive the messages from the server. The receiving is one part, maybe they received but haven't opened the message. Once they open the message, they will also send the read receipt with message ID and the timestamp when that was read. Whenever, let's say, the message was read, the server needs to also update the read receipt with the message ID and when it was read, so that the sender, who's on the other side, also knows when the message was read. Also, the client and server need to maintain the presence heartbeat between each other every, let's say, 5 or 10 seconds. So client will check whether the server is still available, and similarly the server needs to check whether the client is available, because maybe you close the app on your phone or you close the browser tab of WhatsApp, and in this case the connection needs to be closed to not waste the bandwidth. For uploading the media files, we will handle this through a REST API. For example, for uploading a file, we will use a post endpoint, something like /API/media, where we will send the file type, the size of the file, and also, of course, the file and conversation where this file is uploaded to. So this will be sent to REST API, which will be responsible for handling the media uploads. And then on the other side, we have also the media storage where this will be stored. So server will respond with the upload URL, the media ID, and when this expires. And after that, the client will be able to send the upload file to the pre-signed URL for the media storage. And once upload is successful, the media storage will just respond with the upload success and the client will acknowledge it. And as a last step, let's say it included the media file to be uploaded, the server will just acknowledge that the message was delivered, or if there was any errors while uploading the file or sending the message, it will send the message delivery failed response with the error message in the body. Now let's cover the multi-device sync. Let's say the user A can have 3 devices and user B can have 2 devices. How are we going to sync messages between devices as well? We have on this side user A's phone, user A's tablet, and user A's desktop. These are the 3 devices for user A. And on the other side, we have user B's phone and user B's laptop. So first thing, let's say first interaction that happens is user A sends a message to the chat server A, and then chat server will acknowledge and display the status as sent for this first message. Since we agreed that we are going to store the statuses of users' availability in a Redis cache, so the chat server A will then ask where is the user B, because let's say this message was sent to the user B. And then Redis responds that user B has two devices and it is connected on server B and server E, each of these devices. The other two devices of first user will be connected. Let's say one of them is connected to chat server C and the second one is to chat server D. So once the chat server stores the sent message, it will also display through the chat server C, which is connected to user A's tablet. It will display the sent message, and the chat server D will display the sent message for user A's desktop. This is how we will sync the same message between three devices of first user. Now let's see how these messages are sent to the user B and synced with the two devices that the second user has. So user B's phone is connected to chat server B and user B's laptop is connected to chat server E. The chat server B will read the message from database and deliver it to the phone, and this chat server will deliver the same message to the laptop. And let's say user B checks the message from the phone, so it will deliver the acknowledgement to chat server B, which sent the message to the phone, after which the chat server B will mark this as delivered for the chat server A, which then it will be able to send to the first user's mobile device and update the status to delivered. And next action that will happen is user B will read the message. So once it reads the message, we will send the read receipt to the chat server B. And then this chat server B will again forward this to the chat server A with the message read status in this case. And then the chat server A will update the status and now it will display as read. And since this is read, now we need to also sync that between the user B's devices. So the chat server B will mark it as read also on user B's laptop, which is here. So this way, the user A's tablet, mobile phone, and desktop, and also user B's phone and laptop always stay synced with the latest data, whether the message was sent, whether it was delivered, or it was read. And in case there are conflicts between multiple devices, we will use the last write wins technique with version numbers to prevent the conflicts. And of course, this is not the ideal solution. First of all, we need to apply optimization here. For example, this can be incremental sync because sending the entire message history to a new device is expensive. Let's say we are syncing with this chat server B and user's phone and also user's laptop with chat server E. We don't need to send the whole history in the device. So instead, the device can request messages for last 30 days. Like most users only need the recent history, and older messages are fetched on demand when needed. When they scroll up, the user scrolls up and then the old messages will start to load. And very old messages will be archived in cold storage and they will be loaded lazily. Adding this multi-device sync comes also with a trade-off because we need to support roughly double of the delivery workload. Each message goes to multiple devices per users. But that is an important feature of chat messaging app like WhatsApp because users demand the same messages, the same chats to be synced between their mobile phones and between their desktop apps. Now let's see the core flows on how messages actually move in case of users both being online and sometimes one of the users might be offline. So let's start with both online version. In this case, user A, let's say, sends the message to user B and it's connected with the chat server A. Message goes through WebSocket and reaches to this chat server. Now this chat server will generate the message ID, which is a unique ID timestamp based for this message. And then it will send the acknowledgement with status of the message being sent. Then this server will push the message to the message queue for persistence. After that, we need to check where user B is and which server it's connected to so that we can forward this message to user B. And we can check that from the Redis cache where we have the user connection cache. We will read where the user B is from this cache. And then let's say it responds that user B is on server B. And once we have that information, the server A can route message to server B via Redis PubSub model. And on this side, we have the server B and user B connected with WebSocket. So server B will now deliver message in real time and user B's device will acknowledge the delivery. Next, we need to let the first server know that the message was forwarded and delivered. So server B will make a request to the server A acknowledging the forward delivery, and then we can update the status with delivered instead of sent. And then whenever user B opens the message, the same process will repeat and we will now mark the message as read instead. And optionally, we can also enqueue the message for analytics or archival by using async processing between server A and between the message queue. And meanwhile, the message queue will be writing the message to the message database like Cassandra for storing the history. Now let's see this same flow, but in case when the user B is offline, which makes it a bit harder to manage, but still we need to make sure that the message is received and we also notify the user B when they received, even when they were offline. So the initial steps are the same for this situation. User A sends the message to user B through chat server A, and then we check whether the user B is online from the Redis cache. And in case the user B is offline, which is our situation here, we will add the message to user B's inbox with Redis, and then we will store this in inbox table in the database inbox. And after that, this chat server will connect with the notification service that we have here and send push notifications for user B. Once the notification service receives the message, it also triggers push notification through Apple's or Google's notification system. And then we enqueue the message for further processing to the message queue. And after that, message queue will persist this into the database. And once the user B comes back online, let's say they open the app and establish the WebSocket connection with chat server C, we will forward the message for delivery to the chat server C, which has the WebSocket connection with the user B. And after that, we will deliver the message in real time to the user B's device. In case user B was online during this time, we will just forward the message for delivery to the chat server where the user B is connected. Let's say it's the chat server C. But if user B was offline first and now they become available, this is the flow that we will have. So let's say user B comes online after being offline for a while. We already sent the push notification and they connect to one of the chat servers like chat server C. First thing we will do from this server is we will retrieve the pending messages from the inbox from Redis. And if there are any messages that are pending, we will retrieve them, any missed messages from the database inbox, and we will deliver the pending messages to user B. And similar to the previous flow, we will also notify the user A that the message was read. Next, we need to design this for group messages as well and see how we can handle 50 to 100 person groups in WhatsApp. This is how it will look like at a high level. Let's say we have multiple users in the same group chat. We will first of all need a group service which will be managing these groups. And as an example, let's say user A is part of this group and we have another 50 to 100 persons in this group. First flow is when user A sends a message to the group. Let's say for each group we have ID as we described in the data model. This gets sent to the chat server where they are connected. And then the chat server, first request it will make to the group service is to check who's in this group, which is ID of 789 as an example. And it will retrieve the list of users like user IDs who are in this group, part of this group. And after that, we can check the status of these 50 users. We can use Redis to cache the status of users to not waste the database queries for reading this. And let's say we check the status of the 50 users and find out that 30 of them are online and the rest, the 20 other users, are offline. For each online user, we need to look up which chat server they are on. So we will publish to channel user1, user2 to user30 to the Redis PubSub model. And then this will parallelly deliver to online users. Whoever is online, they will receive their messages in their own chat server where they are connected. Let's say 15 of the users are connected to server B and the other 15 are connected to server C. We will in parallel distribute the message to both servers, and then these servers will distribute them via WebSockets. So it will deliver via WebSocket to the 15 users from server B and to the other 15 users from server C. For each of these deliveries, they will acknowledge from user's device that the message was delivered, and same for the other 15 who are connected to the other server. And then we will forward these acknowledgements to the server A, which originally sent the message, so that it can update the status of the message to sent or delivered in the user A's device. For the other 20 users who are offline, we need to use the same thing generally that we did for the offline users in one-on-one connection. We'll need a Redis inbox where we will write the messages that they need to receive, which is, let's say, these other 20 users who were offline, we will write it to user inboxes. And we will write to 20 inbox records in the database inbox. And for all of them, we need to send the push notification either through Apple's or Google's push notification system to notify them through notification service that the message was sent in the group. And then the notification service will push this through either Apple's or Google's notification system. So this way we are just storing message once. So we are doing one write operation from chat server A, which received the message from the user, to the message queue. And then message queue writes this to the database. So eventually it is just one write operation per message. And lastly, we will also update the status that it was delivered to 30 and it is pending to 20 users for the user A's device. Now, so far we haven't covered how we are going to manage the media files, the image assets, the videos, so let's cover that next. Of course, the wrong way here will be to clients upload the image to the chat server and then chat server store it in database and then recipient downloads from chat server. This is of course not scalable. Your chat servers are now bandwidth limited by file transfers, and they are not doing what they are good at, which is routing messages quickly, and instead they are doing what they are terrible at, which is moving large blobs around. So the right approach is using pre-signed URLs. And for all these technical terms like pre-signed URLs, notification services, Apple's notification service, these kind of things will be included in the footnotes. If you're not sure what they are, feel free to check it there. So let's look at the correct approach for uploading the media files. Let's start with the upload flow. This was the basic design of the messaging app like WhatsApp. Of course, there is way more to this, like we need to also now scale these to billions of users and handle disasters and recover the parts of the systems which fail. We need to implement security practices, abuse prevention, rate limiting, and much more. All of this is covered in the next part, which is only in the mentorship program. If you're watching this on YouTube, in the mentorship program, we have these and many other systems like designing YouTube, designing Twitter, and other systems from scratch in detail like this. And you can see all the footnotes also about each technical concepts that I use, so that if you're not sure how pre-signed URLs work, if you're not sure how CDNs work, how to set them up, these are all the materials that will help you to get to a point where you can confidently design such systems from scratch during interviews or during your work for certain features of the system. So all of it is in the mentorship program, which will be the first link in the description. See you next time.